So yes, I'm Francesco Duronio from University of L'Aquila. I'd like to present you this work regarding hydrodynamic cavitation simulated with the Lagrangian particle breaking method. And I'd like to start pointing out motivation behind this activity. And I can say that historically cavitation was regarded as a negative phenomenon. No, all of us know about erosion in propellers and so on. But I reported this cover of Nature. All of us know Nature, and it says bubble power, because actually these cavitation bubbles has also some power within them, and we can kind of exploit cavitation phenomena for some positive effects. Professor Suslik was one of the first that have done this. But let's move on and try to understand. Okay. A little bit more about cavitation. It consists basically, as all of us know, on the formation and of vapor bubble that takes place when obviously saturation pressure falls below the ambient pressure, and when the normal pressure conditions are restored, this bubble collapses, and this is the part which interests to us. Because during this bubble collapse, there are extreme conditions with the temperature and pressure. I reported here some values, and this condition triggers the hydrolysis. So we basically get from water OH radicals and other species, but these OH radicals are really important because they can be used to make chemical processes, and they can be used, this OH radical, within advanced oxidation processes. And for advanced oxidation processes, we can mention for sure the production of, through advanced oxidation process, we can mention the production of biofuels. We can use this process on the food industry. We can use this process in these processes in many other conditions. I just want to mention the most important one, which is the purification of water, of wastewater, because I say that for sure the most important, because water quality is an important concern. And as I'd like to show with this graph, this image, it is still today an important reason of death. As it's written here, mortality is still relevant due to the unsafe water usage. But at this point, we need to trigger this cavitation phenomena. And we can trigger cavitation phenomena basically using these two methods. The first one is using sonic waves, and so ultrasonic method, or acoustic cavitation. But also we can force a liquid flow to pass through a null, a convergent, divergent like shape, ducts, and this is basically a Venturi tube. And this is hydrodynamic cavitation. I reported. This is the sound of cavitation, and this is our experimental facilities at the chemical plant laboratory of L'Aquila, and this is actually doing hydrodynamic cavitation. This is for the purification of wastewater, And this is the main. This Venturi tube is the main actor of this phenomenon. And this technology today is present only at laboratorial scale. We don't have industrial application of hydrodynamic cavitation. And for this reason, we need proper tools to develop this technology and to bring it to an industrial scale, optimizing all the main parameters. And for the purpose, we decide to develop an ad hoc CFD solver, obviously with using OpenFOAM. Which are the ingredients, what we need, and what we expect to get from this simulation. We need to simulate a multi-phase flow. We are interested in the local. It's kind of most important thing of this solver should be the capability of representing the local bubble properties. And I'm saying among the many, the peak of the pressure when the bubble collapses. So I can say also peak of temperature, bubble radius, and so on. So we need to solve the complete Rayleigh-Flessey equation. And so the idea behind this solver is kind of make the opposite of what we usually do, at least for SPRICE, with the Lagrangian methods. So we decided to use a Lagrangian particle tracer, not to follow liquid particle, but to follow vapor bubbles. And instead, the Eulerian framework was exploited for studying the liquid phase. No, okay. So, and you can see what I'm saying here. Okay, this is the bubbles, and this is the Eulerian framework. One-way coupling method was obtained through the pressure field that was used for the Rayleigh-Flessey equation. But let's go on a little bit in the details of the equation. Just few hints. This is these are the Navier-Stokes equation we solved for a mixture of vapor and liquid. These are solved for a barotropic fluid. Sorry, they are solved for a barotropic fuel. These are the equation of state, and I here represented the equation of state for water. And from solving this momentum conservation equation, we get the pressure field, which we can fill in the complete Rayleigh-Flessey equation. So we are able to solve the Rayleigh-Flessey equation and to get the bubble pressure development in time. This must be solved using a Runge-Gupta method. And this is solved obviously with together with the other governing equation of the particles to follow. Obviously, they traveled within the integration domain. Bubble injection is controlled by two parameters: a spatial density and a temporal frequency of the aperture of the bubble And we decided to call this solver cavitating LT form. But at this point, we need to kind of validate what we have done, and we obviously consider a Venturi tube, two cavitation regimes, the reentrant jet and the condensation shock regimes, and we exploit shadow graph experiments and computed tomographies, and we can see how both Strual number, cavitation number were pretty well matched by CFD simulation in comparison with the experiments. But also we can observe from these computed tomographies, these are sliced taken at these places, A, B, C, D, and so on. And this is the CFD simulation. We can see how actually there is a pretty good agreement between the two data sets. And this is quite comfortable, together with the fact that we can, as you can observe, we had also estimate the numerical uncertainties using the classical roach approach, and we plotted the axial values of the pressure and the axial velocity fields, and we can observe how actually the error bars are quite small, and this is quite good for us. This was done obviously simulating the same condition with 3 different levels of grids, and the fine one ends up with a grid of 0.25 millimeter in the cross section. Okay, this is a visual qualitative validation, and we can observe how the evolution of the vapor predicted by the CFD is in a good agreement with what we see from the shadowgraph experiments, and we can observe how the re-entrant regime is shedding cycle is quite shorter if compared to the condensation shock shedding regime, which lasts for 22 milliseconds. And this is quite good. And at the end, we can also say something about the flow field characteristics. The particular feature of the re-entrant jet is the fact that we have near these walls, these Venturi tube walls, we have these recirculation zones, and the fluid comes back to the throat section, as we can see from these negative values of velocity. And this doesn't happen with the condensation shock regime, where vapor is shedded all over the Venturi tube. But at this point, we need to move to an actual chemical application. And for us, the chemical application is the coloration, the purification, the removal of this methyl orange pollutant from wastewater of the textile industry. And this is the sketch of the experimental the experimental setup at the chemical plant laboratory in L'Aquila, where the decoloration, the methyl orange, as I said, was tested on different pressures ranging from 3 to 6 bar, using this Venturi tube, which is the same I showed you previously. And these are the characteristics, geometrical characteristics, and we obviously simulate this condition using this situation using our solver. And we can see initially how the cavitation number experimentally measured is in quite good agreement with the CFD simulation. And we also come to the Strull number. But let's move a little bit on. And these are other experimental images, and we're gonna observe how actually increasing the inlet pressure, the amount of vapor shed released from the throat section increase. And this is okay. This is good because it replicates what we observed from the experimental observation. These are another time flow field configuration, and we can observe how there's no evident clear zone of recirculation. The flow, it seems a little bit more how can I say, unstable. Not so. There is this central plumb, but near the turbulence as a relevant role. But I'd like to arrive to some chemical consideration. Okay, these are the experiments where we measured the decoloration of the how much we remove our pollutant from the initial solution. And we can observe from the blue curve that there is actually a maximum. And this is quite interesting because, as I showed you previously, it seems like we saw both experimentally and also from the SFT simulation that the amount of vapor generated increases with the pressure, but the efficiency, it doesn't increase. Cavitation number decrease, and it's okay. And to understand why this happens, we exploit our CFT code. These are the Lagrangian particles, Lagrangian bubble, let me say, for tested pressure. We can see how actually the peak pressure at the implosion of the bubble remain more or less always around 400 bar, but the number of parcels generated increases drastically. So why we are facing this decrease of hydrodynamic cavitation efficiency? Okay, the reason is that, as you can see from these 5 and 6 bar snapshots, the bubbles like to form, like to merge one with the other, creating this bubble cloud. And this bubble cloud is quite known from the chemical perspective of studying cavitation, because these bubbles, which are really close one with the other, like merge one with the other, and we have basically coalescence that at the end triggers radical recombination, and this radical recombination makes the OH radicals to recombine with the other part of the other species and to form back, to give back the water molecule. And we don't have we still don't have anymore the efficiency for having a chemical reaction of purification. So let me conclude saying that cavitating LP foam is a Eulerian Lagrangian code to study hydrodynamic cavitation processes for application to chemical or advanced oxidation processes. It features the complete solution of the Rayleigh-Plesset equation. It was validated against experimental data. And also we applied this method to study the decoloration of organic substances using different inlet pressure. Increasing the upstream pressure, we understand how structural number, cavitation number decrease. The peak of pressure remains more or less all the same, of about 400 bar. And with increasing pressure, coalescence phenomenon plays an important role because they trigger the combination of OH radicals, diminishing the decoloration and the hydrodynamic cavitation efficiency. Thank you.
Thank you very much for listening to the talk.
Hi. This is actually one of the next steps, because I haven't already implemented a kind of a coalescence model to treat this condition. Because it's the question is, can we use a classical coalescence model to simulate, to model this recombination of these bubbles, because these coalescence models are usually used for liquid parcel, and we are talking about vapor. And so I am looking forward to implement a coalescence model. Otherwise, it will be difficult to match that behavior of the decoloration efficiency. You're welcome. Yeah, good question. Thanks. Please go ahead. Okay. Yeah. Okay. So the answer to this question, it relies on this equation, because getting the pressure field, we basically solve the Eulerian equation, and we get a pressure field. Next, we fill up the pressure field in the complete Rayleigh pressure equation, and we need to solve this complete Rayleigh pressure equation. Otherwise, we, as done in all the cavitation, many, not only, most of the cavitation models, we consider this bubble pressure as the saturation pressure, no? And we delete this term, and this term, and we get a cavitation model. But we need to understand what happens in this bubble pressure, and also in this radius. So you can kind of relate this bubble pressure to these other terms, and you can see here the saturation pressure. So you basically have a system of two different ordinary equations. If you integrate these two equations, so this system is, if you solve this system, you will get the radius as a function of time, and this radius say to you how the bubble grows and collapses. And together with, let me say, together with adding this other governing equation, you can move your particle simply using a drag force expression towards the through the domain. And that's all. I hope I answered your question. Please. Yeah. Okay. So you basically are asking. So you basically are asking if let me sorry, understand if I get your question. This is a bubble. If this bubble grows larger than a cell, what happens? Yeah. Okay. I try to answer your question. About the grid, as I said, I used this 0.25 millimeter. So we have here like we have 10 cells and so on. And you were saying that if the bubbles grows larger, but it doesn't happen because I can say you that I don't have actually here a plot about the evolution of the radius versus time, but I can say you that we are talking about tens of microns. at the maximum, like 50, 60 micron. So it is always smaller than the main issue of this approach is to define these two parameters, because no one can measure the bubble departure frequencies and the density of space. These are.
So good afternoon. And, today I try to present a topic that maybe is not so common during this conference. So let's talk about precipitation. The measure of precipitation, be it rainfall or snowfall, is actually very important for our modern society, since it affects a large range of fields. And its measure is usually obtained by mean on the ground by mean of precipitation gauges. And those can be divided into major categories: the catching type gauges that require a funnel to collect incoming hydrometer. Those are relatively low-cost instruments that use very simple functioning principle to evaluate the volume of precipitation, and are also easy to maintain, and therefore were widely adopted by national weather services. However, they only provide the precipitation intensity. Instead, a new family of precipitation gauges called the non-catching type gauges is quickly gaining momentum. Those do not require a funnel. Instead, often use indirect methods to sense incoming hydrometers contactlessly. However, they have a much higher cost since they use very complex measuring principle that, however, makes them requiring very little maintenance. They are also able to provide the particle size velocity distribution of a precipitation event. And for this reason, they are quite interested. They receive quite a lot of interest from both the scientific community and the national weather services. And here I placed on the bottom some example of these kind of gauges. So, like all gauges, they can be affected by a bias. And we have two major types of bias for precipitation gauges: the instrumental bias, that is due to measuring principle and construction of the gauge itself, and can be mitigated by means of calibration of the instrument. Then we have environmental bias, and this is due to the environmental conditions that are found close to the gauge body. And those can be mitigated by means of correction curves. And regarding the latter, wind is the primary source of environmental error in precipitation gauges. And this is so that because the gauge immersed in a wind field behaves like a black body object and creates strong velocity gradient close to the collecting area or the sensing area of the gauge. And those velocity gradient can divert incoming hydrometer trajectories and therefore produce a bias in the measurements. And this effect is actually known by more than 150 years. And some other solutions are known and used. However, those are applicable only for test sites, like in the picture that I placed here. Here, the instrument is placed below ground so that is not affected completely by wind. However, in more traditional installation, there is still the need to evaluate this wind-induced bias. And we have some methods, like field intercomparison between reference gauges, wind tunnel experiment. However, in this work, I try to use numerical simulation to evaluate this kind of breeze. And so, we said that wind diverts incoming hydrometers, and the parameter that can be used to quantify the wind-induced bias in this case is the catch ratio. And here is defined as the ratio between the number of drops that are actually collected by the gauge in windy condition and the number of drops that would have been collected by the gauge if it was transparent to wind. So the actual number divided by the theoretical number of drops. And so this catch radius is obtained once the trajectories that fall inside are known, and therefore the equation of motion of each droplet must be solved. However, before this can be done, something must be said about the drag coefficient. In fact, larger liquid drops behave quite differently than rigid sphere that are often used as for the analysis. And so in this work, a dedicated drag model for drops was implemented in OpenFOAM. And here I place a little comparisons between the model implemented here and a simple model already implemented in OpenFOAM for a rigid sphere. And however, since it is a new model, some validation is necessary. And so validation was obtained by means of experiment inside the Politecnico di Milano wind tunnel. Here, drops were released close to the gauge body, and trajectories were measured. And so let's talk about the experimental setup. For different gauges, they were put inside the wind tunnel, and using a calibrated nozzle of 0.2 millimeter, small drops were released directly into the wind flow. The trajectory of drops was illuminated by the strong light, and trajectories were captured using a high-speed camera with a resolution of about a special resolution of 0.25 millimeter. So different speeds were tested between 8 to 13 meters per second, and trajectories were captured using two different frequencies, 10 and 1000 hertz, by the camera. So the camera gave us a lot of images, frames, and those were post-processed. So the images first were reduced to a simple black and white scale, and the background is removed by subtracting the luminosity of a empty frame. So then a combination of Gaussian and Laplacian filter was applied to pre-process the image. That was then binarized using a threshold so that the background is completely black, and instead the droplet is highlighted in white. And so depending on the type of frame, for the high frequency frame, a vertical moving windows was used to identify the drop in the drop center in each frame, and combining a multiple of this frame allowed to compute trajectories. While in the case of the low frequency frame, since a streak is captured, a skeleton filter provided the middle line streak of the drop trajectory. And so here an example of the results obtained in the upper part, the results for the high frequency acquisition of 1000 hertz, and here both the position and velocity of drops is obtained. And while in the second case, you see in the video that you can, you see the streaks that are seen by the camera. And so those can be post-processed, as I shown, and then plot. And so in the two images, we see results in terms of trajectories for two different gauges that were tested. And in both cases, we see a considerable deflection of trajectories. And in some cases, it's possible to observe some trajectories like this one that would have fallen inside the gauge collector if no disturbance was present, but instead fall outside of the gauge collector. And this is the source of bias. So during testing, drops between 0.7 and 1.2 millimeter were released, and even if it's a small interval, they actually account for about 30% of the total number of drops that are present in a precipitation event. And we expect, and they are quite influenced by wind, since they have a response time very low, like of about 0.4 seconds. So the measurement campaign went quite well, and the experimental setup showed that is capable of good repeatability in terms of same drops trajectories that show very little difference between one another. Also, as expected, different diameter drops behave differently since they are affected differently by wind. And in general, the difference between simulated and measured trajectories are compared with the drop diameter, showing a very good result. So it was possible to conclude that the drag coefficient and the numerical model used is actually capable of capturing the trajectory of drops released near the complex shape of a precipitation gauge. So then the next step was to apply this numerical model to an actual precipitation gauge. And since for a traditional catching gauge, some correction curves are available, while for newer non-catching type gauges, no correction are currently available, it was decided to investigate the TIS laser precipitation monitor. This is an optical non-catching type gauge that use a laser beam to measure both the diameter and full velocity of hydrometer that cross its sensing area. And the presence of a bias for this gauge is actually well documented in literature. However, no correction curves are available. So in a previous work that I actually will present in the next session, both Urans and LEST simulation were run for this geometry, considering different velocity, direction, and environmental condition. And those were used as an input for this work. So in this work, I evaluated the performance of two different Lagrangian particle tracking models that were both implemented in OpenFOAM. The first is a simple uncoupled model already present in OpenFOAM, where velocity field is fixed, and here I use the average velocity. So trajectory is computed only after CFD simulation has run, while the other is a one-way coupled model where velocity evolves in time and trajectory are computed together with CFD solution. However, in both, no particle-to-particle interaction was considered. All simulations were run until all particles had fallen well below the instrument sensing area or exited the domain or impacted the instrument surface. And all trajectories were saved so as all the impact points on both the gauge body or the instrument sensing area. And drops were released in along a variable spacing grid inside the computational domain. And this grid were placed in space, considering that computing back a trajectory from the center of the instrument sensing area to the center of the grid, so that the grid actually fall perfectly in the center of the instrument sensing area, and the results can be then used. So since gauges are present in the field are subjected to very widely different environmental conditions, 11 drop size, 5 wind speed, and 9 wind direction were tested. And combined, they result in about 500 individual simulations to be run. So I use bash scripting to automate this process. And so starting from an initial case of one combination of the 3 parameters, 3 loops were used to cycle, changing first the kinematic cloud properties dictionary to change the drop size, then the U dictionary to change wind speed, and then the constant folder to change the mesh that and so the wind direction. And of course, after each run, the all trajectory impact point were saved. Also, it was noted that to obtain a strictly one-way coupled model in OpenFOAM, I had to write a new solver that was constructed combining the UNCOUPLED kinematic partial foam and pimple solvers. And so let's start to see some results. Since we have a wide range of drop sizes, so from 0.25 up to 8 millimeter, depending on their Stokes number, they can be affected quite differently by wind. For very small drops, the response time is about 1/10 of a second. And so, considering their terminal fall velocity, they can be affected in as little as 8 to 10 centimeters. While for very large drops, the response time is much higher, 1 to 1.5 seconds. And so, since they also fall quite, they have a higher terminal velocity, they are affected in about 10 to 20 meters. So we expect quite a disturbance for small drops and actually very little disturbance for large one. However, it is worth noting that small drop constitute the majority of all drops that are present during a precipitation event. And so the bias actually could be quite high. And so here there is some trajectories for 0.25 millimeter drops for the 3 different model run that were obtained. The first is the uncoupled model using results from the UNCOUPLED simulation, and here all the about 500 simulation were considered. Then the same uncoupled model was used also on the less simulation. Here only 2 wind direction and 2 wind speeds were available. And then here the average flow velocity was used. Then the one-way coupled was run combined with the less. So here instead of the instantaneous velocity is used. And here are some examples. So differences are actually quite notable, even if the general behavior is very similar. So 2 cases are presented. The upper row is for wind direction parallel to the laser beam of the gauge, and here quite a lot of shielding is visible due to the gauge body itself. While in the second case, the wind direction is perpendicular to the laser beam, so here very little shielding is present. However, especially considering the one-way coupled less, quite a difference is visible due to the small-scale turbulence that is produced by the gauge body. So we've seen how the catch creator is computed, and here results are presented as a function of the particle Reynolds number. And first of all, I've seen that all results were quite well fitted by a second-order inversal polynomial. And this is quite useful for providing to the end user correction curves. However, let's see the actual results. So for a wind direction of 0 degree, we see a considerable amount of bias. Small drops in some cases can be completely missed by the gauge. So for example, considering the yellow and orange lines that represent the higher wind speeds, here smaller drops are actually not sensed by the gauge at all. Then by changing wind direction, we see a notable change in bias that is reduced notably, with that for 22 degree is as high as 80%. Then for 90 degree, we actually see an overcatch. So the number of drops that are sensed by the gauge is actually higher, since they are due to the trajectory. Some drops can actually reach areas of the sensing area, the laser beam, that normally are not accessible to vertically falling drops. And then, of course, in the case of a wind direction of 180 degree, due to the shape of the gauge itself, that is as an electronic box behind, quite a lot of disturbance is present, and also quite a lot of blockage is had. So in this case, for example, for a wind speed of 20 meters per second, the instrument is incapable of sensing a precipitation. Then we can try to compare these results with the other 2 models. So considering the larger dissimulation uncoupled model, we see that for both a wind direction of 0 and 90 degree, limited differences are present, especially in the case of wind direction of 0 degree. While for the 90 degree, most of the differences are present only for the very smallest drops. And so we can say that the larger dissimulation uncoupled approach do not provide a significant improvement in this analysis. Instead, for the larger dissimulation one-way coupled approach, all catch ratio are actually quite lower than the one from the URANS simulation. And this is due to the small scale turbulence that in this case we see have quite an effect on drop trajectories. However, since it's due to turbulence, it depends on the instant in which the drops are released in the domain. And so actually here the only way to have a definitive answer is to run a large number of these kind of simulation, releasing drops at different time steps, so that we can verify if this is a normal, we always have an underestimation, or it's actually due to turbulence, so we have sometimes underestimation, sometimes overestimation. However, the cost of such analysis is actually above the resource that I have. And so in conclusion, during this work, a Lagrangian numerical model with a new drag coefficient formulation was validated by means of a wind tunnel experiment, reproducing drop trajectories near the collector. Trajectory reconstructing using two different approaches, so very little difference, and using previously computed velocity field, two different approaches were run. And it was observed that the less uncoupled approach do not show significant improvement over the much cheaply Urans uncoupled approach, while the less one-way coupled approach show notable effect of small-scale eddies. And so here I left you with some literature that you can check, and I thank you very much. Yeah, but this kind of gauges, the non-catching type gauge, actually measure particle size. So they are actually easier to correct because some of them actually also measure wind. So in theory, the instrument could actually measure and correct itself if, of course, all the correction curves are implemented in the software. However, for sure, it is necessary to have a measure of both wind speeds and direction at the height of the gauge. This is not always, sometimes yes, but sometimes no. So it's still a work in progress.